Okay, good. We are continuing with the topic of light, right? We've already talked to some extent of light, and now we're moving on. Okay, you all have experiences. You probably experienced this this morning, right? I'm just checking out your hair. If I look at your hair, I can tell that every one of you has experienced this at some stage through the day today, right? Looked in the mirror, combed your hair, and what happened was the distance from the woman's face to the mirror, let's say it's 2 feet. What is the distance from the mirror to the woman's face in the reflection? Let me rephrase the question. The woman is standing 2 feet in front of the mirror, right? In real space. In virtual space, if you will, or in mirror space, how far is her reflection behind the mirror?
It's right there. There's no depth. What?
Okay, let me rephrase the question. Oh, that's interesting. Okay, so for now, let's consider the mirror is the back of the glass. The glass is basically silvered, and that's the mirror, right? So, if the distance from her face to the mirror appears to be 2 feet measurable, how far behind the mirror does her reflection appear to be?
Comparatively, it's 2 feet.
Good job. 2 feet, right? Extra credit to all of you who spoke up. In a sense, what you said is correct, right? In a sense, what you said is correct. In a sense, what you said is correct. But the standard level 1 physics answer is what you guys said. The distance from my nose to the mirror is equal to the distance from the mirror to the nose in the reflection, the apparent distance. But it's true, you can't go into the mirror and like measure distance and all that. But okay, so we'll see why this is in future slides. Now, reflection, you all know what the phenomenon of reflection is. It's a return of light rays from a surface. So light from her face goes to the mirror and reflects back to her eyes. And that process is what creates what we call a reflection, at least her reflection in the mirror. So the law of reflection states that the angle of reflection is equal to the angle of incidence. So here is the mirror. Here's the normal to the mirror. The incident ray of light is coming into the mirror at a certain angle of incidence. So let's say that's whatever, 45 degrees. The angle of reflection will be exactly the same as the angle of incidence. That would be 45 degrees as well. And the reflected ray is bounced, if you will, off of the mirror, heading out in that direction, right? So using this law of reflection, this is how we get the fact that the distance from the object to the mirror is equal to the distance from the mirror to the image. Here's the object, light rays coming off of the flame. There's one ray that goes straight along the normal back here, so extend this line. The next ray from the same spot on the candle, in this case the flame, bounces off here and heads out, right? This angle is equal to that angle. That determines the direction that the reflected ray heads off in. You extend the reflected ray back behind the mirror, and the place where that extended ray meets this ray is the place where the flame is in the image inside the mirror. The same thing with these other rays. Here's a ray of light from the flame coming here and bouncing off. Extended this ray back here, and it'll meet the flame, the image of the flame at the same spot here. Now here's another ray of light from this flame hitting the mirror here. This angle must be equal to this angle, so this determines, the fact that this angle equals to this angle determines the direction that the reflected ray heads off in. Extend the reflected ray backwards, and that gives you the image. So each of these reflected rays behaves as if it was emitted by the flame in the image of the candle in the mirror, right? So that's what determines the location, the apparent location of the image. So when you do all of this, you end up with this kind of being mirror symmetric with this. Like all these rays are basically a mirror reflection of these rays. See, this ray is mirror reflected here. This ray is mirror reflected here. This ray is mirror reflected there. That ray is mirror reflected here. Right? I'm sorry, not that ray, but this ray. This ray is mirror reflected here. So this is, if you will, it's a bifold, twofold symmetry, right? Twofold symmetry we've talked about. Don't do this experiment at home, but if you were to cut yourself in the middle like this, right? What happens is, in principle, all these parts map onto these parts, right? So this is bilateral, twofold symmetry. It's as if you have a mirror down here, right? So the same thing here. This is a twofold mirror symmetry, where these rays are a mirror reflection of these. This ray is of this ray, that of this, and so on. So since, let's say this is 2 feet, like in the example we talked about earlier, this would have to be 2 feet as well. This is why the image is at the same distance behind the mirror, apparently, as your face is in front of the mirror. So you can do this like at home, where you step further away from the mirror, and it looks as if the person in the mirror is stepping back, right? That's what's going on. Now, everything that I've said so far applies to a plane mirror, a mirror that's totally flat, straight. Now, you could have a mirror that's curved. If you ever go to a carnival fun house or whatever, and you see there are some mirrors that make you look really chunky or really skinny and tall, right? Or you can have a mirror that makes you chunky this way and squished this way, or extended this way and squished this way. And the way you do it is by curvature of the mirror. You can have the mirror, instead of being totally flat, it's curved this way. Now, you can take a mirror and you can curve it this way, like this. You can also curve it this way, right? Or you can take the mirror like this and curve it this way. That's harder to make, like a saddle. And that's how you get these different combinations of squishing you or elongating you in this direction or in this direction, and so forth. So if you have one of these convex mirrors that's with its tummy sticking out, here's the human. And if you look at the rays from the person's eye, here's the normal. The normal to this part of the mirror is slightly tilted upwards. So this causes this reflected ray to move outwards compared to a plane mirror. And what that does is it causes this reflection to squish in. So what happens is, doing this point by point, his head seems smaller than in real life when you have a convex mirror. Now if you create a concave mirror, okay, concave versus concave, convex. Concave is like a cave, right? That's how I remember that. That's the orientation of the mirror. So you take the mirror, flat mirror, and you curve it so you look like you're going into a cave. In this case, what happens is the normal to the mirror tilts downwards instead of being perfectly horizontal, as would be the case if the mirror were perfectly flat. When you make it concave, that normal to the mirror tilts downwards. So when you tilt, right, see that it's tilting downwards rather than being horizontal. As this tilts downwards, it causes these rays to tilt downwards. So in the mirror reflection, it makes this ray go further out compared to a planar mirror, and that's what causes the person's head to look much bigger, right? So this is a little trick for those of you, I mean, there's probably a market niche for selling mirrors to people who are on Weight Watchers or whatever, right? Where you can make a skinny mirror. The person can go and stand in front of the skinny mirror and say, mirror, mirror on the wall, and so forth, right? And feel good about yourself and go forth and conquer the world. Okay. But seriously, I mean, I've been told that, I don't know if this is true. When I taught this in a previous class, one student mentioned to me that the mirrors in department stores actually do this already. They make people look skinnier. I don't know if that's indeed the case. I would be very interested if you can find some reference that indicates that to be the case, and let me know, right? But it makes sense from a marketing viewpoint, right? Make the person look good, and they're more like, I mean, in their mind. I know, it's a cultural thing. Okay, we'll move on. I'm not making any comment regarding the culture. I mean, those fashions change through the years, right? It used to be in the Middle Ages and so on, that if you look at the paintings of Venus de Milo, I mean, a lot of the paintings from the Middle Ages, a better girth was indication of greater wealth, of greater well-being, and so that was the standard of beauty. Like, so skinny people were kind of frowned upon as malnourished, right? And nowadays, since, well, whatever, that has changed. Okay, let's move on before I dig myself into a hole. Okay, so on the topic of reflection, if you have a totally smooth surface, what happens is the rays all come in and they go out at the same angle. However, if you have a rough surface, you end up with what's called a diffuse reflection. What we see on the surface of our tables is a diffuse reflection, right? I mean, if you look at the surfaces of your tables, you can see a diffuse image of whatever is past this. When I look here, I can see a diffuse image, for instance, of the whiteboard over there, and maybe the periodic table of the elements and so on. If it were a mirror, that image would be very sharp and crisp. But because the surface of the table is rough, what happens is it's diffuse, it's blurred. That's because of this phenomenon where all of the light rays are coming in at a certain angle, let's say, but they go off at a variety of different angles. Now this is making the point that the surface roughness has to be approximately the dimension on the scale of the wavelength of the light that's coming in order to be able to get the light to scatter in a diffuse manner. If those roughnesses are very small compared to the wavelength, as far as the wave is concerned, it doesn't even notice the roughness. So it looks like it's totally polished. So this, you can see right through this, right? Radio telescope antenna. Now to radio waves, this looks like a polished reflector. The waves are large enough that these holes in between, the wave doesn't notice that there are holes. So it thinks that this is a totally polished reflector. And so the waves will actually bounce off of this and get concentrated up there. Right? And so radio telescopes, for instance, you can use a radio telescope to look up at stars up in the sky and look at radio sources in the night sky or in the day sky, whatever, in the sky. And what happens is the radio signals coming in from the stars get focused in here, and you can actually get a radio map of the physical universe. However, light goes right through because the wavelength of light is very small compared to these holes. So as far as light is concerned, this is not a smooth reflector. That's a key point here. Right? So a diffuse reflection is a reflection in irregular directions from an irregular surface, like a rough surface like this. Okay, previous phenomenon was reflection. Right? Now we're speaking of refraction, different spelling. Refraction, not reflection. Right? So reflection, it bounces off. Refraction is the bending of a ray of light when it passes from one transparent medium to another. You've all experienced this with your swimming pool, right? You go to your swimming pool, and what happens is, here's the fish in your swimming pool, and you decide you're going to catch the fish, and you stick your hand in to catch the fish, but it turns out the fish is just beyond the reach of your hand, right? I can say at least one person has had that experience. Extra credit to you, right? So, or more commonly, like you put in one of those poles, right, that you're going to brush the side of your pool with, and what happens when the pole goes into the water? Yep, it looks like it's bent, right? The reason for the apparent bending of the pole that you put into the water is because the light rays travel in one direction in the air, but they change direction when they go into the water. So, for instance, here's the fish. The light ray from the fish travels upwards like this, changes direction to get to your eye. But your eye, the mental model that we project of reality, is based on the assumption that light rays travel in straight lines, right? And so since our mental model that's created by our mind is based on the concept, if you will, that light travels in straight lines, our eyes, seeing the light rays coming in this direction, project backwards here to say the fish is over here, when the reality is the fish is down here, right? And that's a good question. My take would be that the bear is successful in catching fish that are close enough that it doesn't make that much of a difference. That's one possibility. Another possibility is that the bear learns. Either it's pre-programmed to be able to compensate, or it learns. It keeps swiping and it misses the fish, and then finally it says, I need to go a little deeper, I think, right? And there it is. But excellent question, extra credit to you, right? So here's what happens. So here's the normal, which is the perpendicular to the interface between the air and the water. Here is the angle of incidence. The light ray is coming in here, angle between the light ray and the normal. And this is the angle of refraction. What happens is this light ray, instead of traveling downwards in the same direction, what happens is you can see the light ray is bent, right? So what happens is this angle of refraction is smaller in the medium that is more dense, to a first approximation, than the less dense, somebody's pacemaker, than the less dense medium, right? So another application of refraction is you're all aware of mirages in the desert, right? And traditionally, I think in the Saharan desert and stuff like that, like Camel Caravan or whatever, and you look out there and you think you see trees and an oasis, and you get to it and there's nothing there, right? Now here in Phoenix, we tend to not see, and we do sometimes see trees, but not oases. But what we do see on occasion in the summer is you're driving along this road with the asphalt, right, the tarmac, whatever, the black asphalt, and what happens is you look at the road and you see the sky. It looks as if the sky, what the heck is the sky doing down there on the road?
Puddle or something.
Yeah, it looks like this water puddle, right? Because we're used to seeing the reflection of the surface, but when we get close to it, there's no water. There's no puddle. What's happening is this phenomenon. What is happening here is the air immediately above the asphalt gets heated compared to the air above. So since this air is heated immediately in this region, the speed of light is faster here than here. This causes the light wave to bend. So let's say there's a tree here. The rays of light coming from the tree head down, and normally they just hit the tarmac and get absorbed or whatever, right? They'd hit the asphalt and get absorbed. However, because of the bending of these rays of light, what happens is the rays of light from the tree come here, they bend upwards. So when you're looking, so you're driving and you're looking forward in your car, you're seeing rays of light that are not just coming from the tarmac, from the asphalt, but actually are coming from way up in the sky. That's why you see the reflection of the sky, or you see a reflection of a tree or something like that, right? So that is the same phenomenon, the bending of rays of light when you move from one medium, a medium of one density to a medium of a different density. So here what happens is the air near the asphalt is less dense than the air that's further away from the asphalt. Okay, introducing Fermat's principle of least time. Basically, this principle states that light does not really travel in straight paths. It does not travel in a straight line. What it does is it travels in the path that takes the shortest period of time. So it's almost like us. Let's say that you had to drive 20 miles to get here, right? You have a choice. Let's say that your home is at that corner of the class and class is at this corner of the class. You have a choice of either, let's say, driving in a straight line from there to here, or you have a choice of getting onto a freeway, driving in that direction, then switching to another freeway and driving in this direction. The vast bulk of us would actually take the longer path, right? Particularly if you're time constrained, rather than taking the streets, the surface streets that are slower, that may be more direct. So you could add a few miles to your path, but you travel faster and you get here to class faster. Light systematically takes the faster path. It'll actually travel a longer distance rather than the shorter distance if it means that the longer distance gets it there sooner. That's what Fermat's principle of least time states, that light takes the path that gets it there the quickest, but light is in a bit of a hurry. Okay, continuing on with refraction. Here's a pane of glass, there's air on one side, glass on the other side, air on the other side. You have a light source with light coming from that source, from capital A, traveling to little a here. Then the light bends its direction to come over here to this position C. Then it changes direction again and travels this way. Now what happens is, this ray, by the time you're done with this, is parallel to this ray coming in. The light, the shortest path from A to C is from A directly through C, right? However, if light were to travel that shortest path, it would spend a longer period of time in the glass, which slows it down substantially. Glass is slower for light to travel through, and so the light wants, if you will, to spend less time in the glass. Like this is the really congested part of town. So instead of taking the longer path through the glass, which would still be the total shortest path, light travels a longer distance in the less dense medium, in the air, travels a shorter distance in the glass than a longer distance, right? So this is an application of Fermat's principle of least time, and that's what leads to refraction, the bending of the light ray. The light ray comes here, it bends to shorten the amount of time it's spending in the glass, then continues here. So what you're seeing on the other side of the glass pane is an image that is shifted. So when you look out through glass, particularly obliquely, the object that you see on the other side of the glass is not at the same position that you think you see it. It's actually shifted a little bit. And the thicker the glass pane, the more the shift. And the more oblique, right, as opposed to normal, the direction that you're looking at the glass, the more shifted the object is. Kind of like the fish, if you will, right, that you have to go deeper into. Now, we defining something called the refractive index. The refractive index n is equal to the speed of light in a vacuum divided by speed of light in the material. So in glass, let's say, so here is an example for glass. The speed of light in a vacuum is 300,000 kilometers per second. By the time I say 1 Mississippi, light has traveled 300,000 kilometers. In glass, in this particular glass, the speed of light has dropped. It's now 125,000 kilometers per second instead of 300,000. Taking the ratio gives us a refractive index of 2.4. So there are tables of refractive indices, right, for all these materials. So you can just look up the refractive index, divide the speed of light in a vacuum by that number, and that'll tell you how fast how fast the light is going through the glass, for instance. Okay, so using the same principle that basically light changes direction when it goes into the glass, instead of having two parallel surfaces, so it's a parallel pane of glass, you tilt those two surfaces to create a prism. And what happens is, light ray from A, instead of traveling directly through B, it travels in this direction, then horizontal parallel to the bottom, and then turns down to B. Now, instead of just having a prism, you curve the sides, and what you can do is you can make it so that any light ray starting from A but traveling at different angles, when it hits the surface here, it bends through a different amount, such as to make that ray inside the glass parallel to the bottom, and when it comes out, it curves back based on the same principles that we saw here, but in this case curves back to a point B. And what we have just created is a curved prism, which is a half lens. Complete this prism on the other side and you've created a lens. This is how a lens works. So for those of you who wear glasses or contacts, right, what's happening is you have a lens of some kind here, that light from a point travels through a certain point here, its direction changes, this direction changes again, and it comes down to B. And the design of the curvature is such that no matter what angle these rays make, as long as they're coming from A, they will all focus down to this point B. That is a converging lens. It causes light rays that are parallel to converge to a point. Okay, introducing the concept of dispersion. This is the third phenomenon that we are introduced with respect to light. The first was reflection, the second was refraction, which is bending of light. The third is dispersion. Dispersion is where light rays, depending on their frequency, they bend by different amounts. So you got white light, which is composed, as you know, of the various different colors, right? Violet, indigo, blue, green, yellow, orange, red. What happens is when they come into the prism of glass, they bend to different amounts, not all bending by the same angle, so that there's a separation of the rays, the red ray and the blue ray. When they come back out, they bend again, and you end up with the red ray separated from the blue ray. This is why, if you think of crystals and so on, right, glass crystals and stuff like that, and light coming from the crystals, they throw off all these different beautiful colors. Because what's happening is white light from the sun is being split like this into the different component beams, and sending off these different dispersed beams of different colors in different directions. And this is the phenomenon that contributes to a rainbow. What happens is, in a rainbow, you've got line in the formation of a rainbow, right? You've got rain, so there are drops of water. The sunlight coming in from the top there. The sunlight, as soon as it gets into the raindrop, it bends, right? So step number one is the light penetrates into the droplet and it bends. Step number two, it now undergoes dispersion, where two different colors, the beams split. Third, it undergoes reflection at the back of the raindrop. So the reflected rays come out, then again the angle at which they come out is different, and so white light coming in gets separated out into the violet through the red colors. So it turns out that basically this combination for a single raindrop is about 40 degrees for a violet incoming light versus the outgoing violet beam, and 42 degrees for the incoming white light versus the outgoing red beam. Yes, sir?
Now, in each droplet, does it only split twice, or is that just an example to show the dispersion? Like per droplet, is
Okay.
only two colors that come out, or is it?
Oh, there's a whole range of colors between the two, right? So, like the extremes of the rainbow, good question, extra credit. The extremes of the rainbow, we typically see violet at one end and red at the other end. But in between are violet, indigo, blue, green, yellow, orange, red. Each one of those colors, it disperses through a different angle. They're all between 40 and 42.
Okay.
So one would be at like 40.3, the other would be 40.7, another would be 41.1, all the way through 42, right? And that's what creates the separation. So really, there'll be each of those beams coming through here, separated. So if you happen to be, so if you had the sun out here, right? So you're looking at a rain, like a rainbow, cloud over there, raindrops, sun is coming, sunlight coming from this direction. So sun is in this direction, light coming in like this to the rain shower. Here's the person standing, looking in the direction away from the sun, and what happens is light is reflected with all those phenomena that we had mentioned, phenomena, into the person's eyes. So the person then sees a rainbow, an arc, in the range of between 40 degrees and 42 degrees of their eye, right? Now, every little component of the rainbow is caused by, this is amazing, by a different raindrop. So every tiny little...
Sometimes they end, like they'll just see it.
Exactly.
Sometimes they'll be...
Yes. And if it ends partway, that just basically means there aren't any raindrops over there to do this reflecting thingy and dispersion, right?
So how do the leprechauns know where to put the pot of gold?
That's an excellent question. That's why... It's rare for me to be struck totally speechless. Okay, extra credit to you. If you can find out like how the leprechauns anchor the rainbow to bury the pot of gold there, totally.
Give you the million or 2 million.
That would be it would be nothing to you, right? Yes, but extra credit. Okay. So the amazing part is every single part of the rainbow is coming to us from a different raindrop. So is every single color, right? And not only that, if I kept looking in a certain direction, I see red on the rainbow right over there. At every given instant in time, it's a different raindrop. It's not the same raindrop. So it's a fairly constant phenomena by cooperative behavior, if you will, of a whole bunch of the raindrops and so on. Okay, now there's something called the second. Do you guys see the secondary rainbow or the second rainbow? Right? So here's the first one. It's the brightest, and there's the second one, and it's not as bright. In principle, you could have a third one, and so forth. But what happens is the higher orders are dimmer and deeper. So it's very rare to find a third rainbow, fourth rainbow, and so on. What's happening with the second rainbow is this: the light coming from the sun is now coming into the raindrop at a slightly different angle. It disperses, reflects off the back once, reflects a second time off of the back, and comes back out and disperses into red through violet. So in this case, what happens is the colors are inverted. So we got violet on the left here for the first rainbow, red on the right. The second rainbow, red is on the left, violet on the right, but it's much dimmer, right? So this is with two reflections. So in principle, if you could set up 3 reflections and so forth, you could end up with a third rainbow and so forth. Now the reason why the intensity keeps dropping is because every time it reflects off the back of the droplet, some of the light is lost. Some of it gets transmitted through. And so the intensity of the beam coming in here, let's say this is 100 units. Okay, the beam comes in here at 100 units. Let's say 50 units gets into the raindrop. Let's say 25 units gets lost. So that beam is just 25 units. Then another 12 units gets lost. So the beam coming out is like 10 units compared to the initial 100 units. Right? Okay, that's the same image that we saw. And this is basically the first raindrop, the rainbow, and this is for the second rainbow.
So is there any reason why the rainbow actually happens in this next spot as opposed to a different area?
Why the rainbow happens at a particular spot?
Like that, well, at that spot. Why is it like that?
Now, the rainbow is defined by these angles based on the observer. So what happens is, let's say you're there. Let's say that the rainbow is occurring on this side of it, right? And let's say I'm standing here. The rainbow that you see is not the same rainbows that I see. The one that you see is an arc that is drawn starting from your eye at 40 degrees and going up to 42 degrees. So just like with a compass, right? Draw an arc at 40 degrees, draw another arc at 42 degrees. And the rainbow is in between those two arcs for you. For me, the center of these arcs is here, not there. So the rainbow, even though we're standing next to each other, what happens is the rainbow that I see is shifted by that same amount. So it's a different set of raindrops that is creating the rainbow that I see, right? So what is really defining the location of the rainbow that you see is the fact that that 40 to 43, the reflections, right? So those angles, that 40-degree angle and the 42-degree angle, that is what determines where you see the rainbow, right? So if I was standing here, here's Wendy and there's you, each of us will see a rainbow over there. We will talk to each other about that rainbow, but the rainbow that we're seeing is not the same rainbow. Isn't that interesting? We think it's the same rainbow. It's not. Each of them are shifted a little bit. And the raindrops that are contributing to Wendy